All right. I don't want to hold up too much time, so I think we'll get started here. Um, I just want to say hello, everybody. Thanks for joining us today on another one of our Tech Talks in our Tech Talk series. My name is Jawan. I'm the event coordinator for AI Futures. I just want to start off by saying, again, thank you for coming. And today, for our guest speaker today for our Tech Talk series, we have Dr. Bill Kiser, and he will be doing a talk on advanced packaging and how it affects AI implementation. Before I pass the mic over to him, though, I want to talk a little bit about AI Futures and what we do. So let's get started here. So AI Futures as a whole is a program funded by the Department of Defense to help educate students like you on the civilian opportunities that are available within the DoD. So essentially with some of our staff that we have, like Markham Pfeiffer and also Molly Spriggs, they'll be able to sit down with you in our info sessions that we host and essentially work with you to, say, develop your resume, fix up your LinkedIn profile, essentially get you ready and show you these opportunities and push you towards some of these opportunities, whether it be internships, full-time opportunities, or even some scholarships that are offered by the Department of Defense. So if this is something that you're interested in, is something that you want to get started with, we have a QR code right here. If you scan that QR code, that will allow you to schedule time with Markham Pfeiffer, our student outreach coordinator, to be able to get into these sessions and start working towards fixing up that resume and going about the various services that we offer. Also, as well, if you can't scan the QR code, we also have outreach@aifutures.us. That is our email that we monitor, so we'll be able to respond to you that way. So going forth from there, I want to start. I apologize. From there, I do want to pass it off over to our speaker to allow the maximum time to allow him to go through his presentation and allow some time for Q&A at the end. And that is something that we're offering as well. There will be some time for Q&A at the end. One thing I do want to ask is if you do have any questions, if you join this through your computer, please send this through the Q&A activity. So if you look at the bottom right-hand side right next to chat, there should be a button called Activities. From there, click on Q&A and submit your question that way. It's easier to manage and see your questions that way rather than through the chat. If that doesn't work for you, you can submit it through the chat, but we're going to kind of advertise the Q&A. You can submit your questions that way. That would be great. So from there, I'm going to pass it off to Dr. Bill Kiser.
All right, thank you, Jawan. Can you see my screen? I'm sharing with the attendees now.
Yes, we
can.
All right, awesome, and you can all hear me well.
Yep.
All right.
Yeah.
So, first of all, thank you so much for spending some time with the AI Futures team on a Friday afternoon. I know as a former undergrad and graduate student that time is precious. So knowing that time is precious, I didn't take it lightly when I was asked to give a presentation to you. And I really, what I wanted to do was be able to tie a couple concepts that you hear about fairly often together and in a way that you probably don't get in a classroom. So the goal today is to really show you how advanced packaging and the evolution of semiconductors is also tied to what we would call this whole burgeoning market in AI. Now, to do that, and I know I have a pretty diverse audience here as far as studies and years of studies, wanted to make sure that you could get enough background and there was enough information there that we could arrive at this final point and we could get to the point where you really understood how advanced packaging, heterogeneous integration is going to dovetail with AI. So really what I'm doing here, I'm going to give you 6 chapters that give you individual threads and pieces of information that all tie together. We'll start out with and it will end up in a culminating discussion of what are the products on the market that enable AI and why are they so important and how can you use them moving forward. Now, like all good books, it should probably start with a foreword. And any time that I get to talk to young people who are starting their science and their engineering careers, I always take a little bit of time to get up on a soapbox and tell you about my career. And not so much about my career, but how exciting it has been, right? There's never been a dull day over 35 years. I've enjoyed every second of it. And part of it is it changes so rapidly. It has been an incredibly fulfilling, lucrative, professional career for me. And like I said, I have seen amazing things. And it's easy to say that, but I kind of wanted to give you a baseline. I want to give you a baseline of where technology was when I was your age. And it does a couple things. It gives you an idea of how fast your career is going to move, but it's also going to explain to you some of the evolution that we've seen in technology. And that's why you see this explosion of applications in AI. So from a computing standpoint, some of this may be a little bit difficult to believe. When I went to college, didn't have a smartphone, didn't have a laptop, didn't have a desktop, right? We did our computing, and if you could call it that, it was rudimentary word processing, some level of computation, a little bit of drawing, and what was called a mainframe, a VAX 11780, right? You had to go and sign up for time on this machine. You sat in a room with 50 other people at a keyboard with a disk drive, and that was it, right? It was incredibly expensive. It's $160,000 in 1980s technology, so this is about $1 million device now. It ran at 5 megahertz. If you were fortunate enough to have a desktop, and very few people were, they were pretty much only at the high school level or at the commercial level, it was probably something like an Apple II. An Apple II ran at 1 megahertz. It had at its best 32 kilobytes of RAM. It was $2,000 in 1980s dollars, which meant it's $6,000 to $7,000 to have this now. So this is a $7,000 desktop. Your gaming console, and there were a variety of them, mine happened to be an Atari 400, ran at 1.8 megahertz, cost $200 in 1980s dollars. Games were $50. What you'll notice about both of the desktop, both the Atari and the Apple IIe, is that there's really not much solid state memory. The Atari came with a cassette drive. That was your magnetic memory that you had for that. And your Atari came with your Apple came with 2 disk drives. These are 5 1/4 inch floppies. One of these is where you store your work. Curiously enough, the other one is where you loaded your operating system every time you turned it on, right? So the operating system isn't even stored on the computer. It's loaded from a floppy. And I don't tell you this because, this isn't I used to walk to school in the snow. This is to really set the baseline, right? This is to set the baseline for what was available 35 years ago. So you saw what computing was like. Let's look at what memory and communications were like. This is a 5 1/4 inch floppy disk, magnetic media. This was one of the primary methods of storage in the 1980s. It had 360 kilobyte. It evolved to 1.2 megabyte. If for some reason you got to the point in the early 1990s that you had complex software, you might have to load up to 10 or 20 of these into your computer just to load the software that you bought in boxes of disks, right? Not very reliable, failed a lot, didn't have great capacity. So solid state memory is not prevalent at this point. You're doing a lot of storage in magnetic removable memory, and doesn't have great capacity. Like I said, there were no smartphones. There were hardly any cell phones. This is an example of a 1989 cell phone. It's a Motorola 4800X. It's about $6,500 in today's dollars. It had a 30-minute battery. That was it. Wasn't horribly reliable, didn't have great coverage, bounced in and out a lot. I would say maybe 0.1% of the people had them, and it was confined to salesmen and commercial applications. Very few people had personal cell phones. I have this nice gray box over here for the internet and the Wi-Fi because they don't exist yet, right? World Wide Web doesn't come around until about 89 or 90. Of course, there is no Wi-Fi. When the web does come on, you really don't get access until the mid-90s. It's done through a 52 kilobaud modem. So, right, you're not moving a lot of data. You don't have smartphones to collect data. And while all you use a smartphone to navigate, our GPS was an atlas, right? GPS was still encrypted at this point. So all of a sudden, there's all these things that are so prevalent to us now that enable AI. They weren't really even available a long time ago. So the lesson I want you to take away from this forward is the computing, the memory, data collection, and comms were a tiny fraction of what they are in the world that you know now, right? And I also want you to remember that technology accelerates rapidly as you look at your career, right? Stay abreast of it. Don't get stuck in anything too long because it offers staggering opportunities for tech professionals. So let's move on to our first real chapter of the book. Chapter 1, the history of AI/ML. I'm sure a lot of you know a lot about AI/ML. Perhaps a lot of you know more than I do at this point. But there's some things that I want you to be aware of because they're really important to understand why all of a sudden AI/ML has come about in the last 5 years. So I'm guessing some of you on the call think AI/ML is something entirely new. It really isn't. Think about the birth of AI. It's done by Alan Turing in around 1950. Alan Turing is the guy who developed the mechanical decryptor that was used to defeat the Enigma machine that the Germans used for communications during the war. In 1950, Turing comes up with what we call the Turing test. And basically it says if a machine can fool you into believing that it's human, then it potentially has intelligence. This sort of languishes for a few years, and people are still kicking around what that means until 1956, what some people consider the real birth of AI. John McCarthy holds a summer meeting at Dartmouth with some Bell Labs personnel and other experts in the area, and they come up with this overall philosophy of what AI is and what it means. The smartest of the smartest were there at the time. I don't know if we have any CMU people on the call at all, but if there are people with CMU heritage or there now, you walk through Newell Simon Hall. That's named after a guy named Alan Newell, who was also part of it and also almost legend at CMU for his contributions to the field of AI. But in any event, out of 56, this is a great new concept, and there's actually quite a bit of investment at this point, both public and private, into the field of AI. This goes on through the 60s, and by the end of the 60s, we as scientists and engineers will say that wasn't really a failure. We learned a lot from it. That's not necessarily true for those who invest in it and expect products. Not a lot had happened in spite of great promise. And we go into almost 30 years of what's called the AI winter. There's very little investment, interest wanes, and only truly the smartest and brightest and determined people stick with AI through that period. Then we get into the late 90s, right? And some things start to happen. Deep Blue comes out. It's an IBM system that played Garry Kasparov, probably one of the greatest chess masters of all time. It actually not only plays Kasparov, but it beats him. IBM also comes up with Watson in 2011, which is after Siri, which is kind of AI to some extent. Any of you know who might have had a 4S at that time know that Siri had a few glitches in it. But also in 2011, something remarkable happens. IBM also comes out with Watson. Watson beats Ken Jennings at Jeopardy, and it's a pretty fair game, right? It's fed text questions while Jennings and the other competitor have to read the text off the screen. But over 3 courses of 3 games, it manages to bury Ken Jennings by, I think it was $27,000 that he beat him by over 3 games. So now we're starting to get some interest in AI. The one note I'll make that IBM is a solutions provider, but also in the background, they are a computer and a semiconductor innovator, right? So AI at IBM is tied really to the hardware and the systems that they are building around the hardware. So I like this graph because it cuts off at 2017, because by 2017, a lot of you really have a very good idea of what's happening in AI. But what you maybe don't know is what the AI market sector looks like in North America, right? Back in 2014, 2015, you're talking about a couple $2 billion. But 2024, 2025, we're expecting $250 billion in the North America AI market size by the end of 2025. That is truly remarkable growth in any sector. So the take-home lessons that I want you to have here, the theory of AI has been around a long time, meaning people really kind of had an idea how to implement it, but it's only been usable the last 5 to 10 years. A lot of that's going to be tied to advances in memory and hardware because as we know, AI requires tremendous computing power, and that's what enables this process. All right, Chapter 2, the history of semiconductors, right? So semiconductors have been around a while also, really founded in 1960. And we're not going to get into the history of semiconductors because we don't have that much time. Two things I would like to offer up to you. So there's a book on the New York Times bestseller right now called Chip War. A very detailed and interesting look into the wild growth, a lot of the commercial wars that took place in the semiconductor industry is from the time it started in the 60s and 70s. And then it also gets into why the United States has lost some of its competitive advantages in this area, how the supply chains have broken down, and how we're trying to onshore some of this work through the CHIPS Act, the CHIPS and Science Act, which is a big multi-billion-dollar effort of the U.S. government to reconstitute semiconductor manufacturing in the United States. Now, one of the people you're going to hear about and read about is Gordon Moore. Gordon Moore, while we'll talk about Moore's Law in the next slide, what you may not know is Gordon Moore was the co-founder of Fairchild Semiconductor, one of the first ones to build solid-state transistors. But he was also the co-founder and the CEO of this other company, which I'm sure you've heard of, which is Intel. Intel has revolutionized a lot of the processor and computer business in the United States and throughout the world. Gordon Moore also came up with a theory. His theory was that the number of transistors on a chip will double every 2 years. And curiously enough, Moore was not far off. If you look at what we have here back in the early 1970s, we have maybe 5,000 transducers per chip. But now, here we are at 2020, we have 50 billion transducers, 50 billion elements per chip. Thus, the speed, the capabilities of computers has grown at this exponential rate over the course of the last 20 years. Now, just to make sure everybody knows, we'll have a real quick remedial lesson on transistors. Remember what a transistor is. A computer thinks through digital logic, which is a series of switches or very simply on and off. If you flow a small current from your emitter to your base, that means that the current from your emitter to your collector can flow. This is a switch. It is on or off. Transistors come in a variety of different forms. They come in a variety of different sizes and capabilities. But the fact of the matter is, the more of these that you have in an area, the faster they operate, the more digital logic that you can perform in your computer. A lot of this is tied to size. A lot of it's tied to architecture. But from a Moore's Law standpoint, computing power is driven just by the sheer number of the size and the number of these elements inside a computer. Now, I love this. It's a little old. It's been around a long time, but I think this is a great graph. It shows two things. It's not just showing you the number of transistors against Moore's Law. It's showing you million instructions per second per $1,000, right? So you can see that if you spend $1,000, the number of millions instructions that you get continues to increase. By 2000, you were getting about 1,000 million or a billion instructions per second for every $1,000 that you spent. Why this is important, why I always thought it was important, is if this line continued, the whole idea that was by 2020 or into 2030, that you would have amount of computing equal to the computing power of a human. So we may get there, but one of the questions you have for artificial intelligence, we're not really going to cover this so much today, do sheer MIPS ever equal sentience? Meaning, is it going to think? Is it going to act like a person? And there's a lot of questions about that. So while you have raw computing power, there's even that next step that has to be taken about exactly how it behaves and how it performs. And sentience is an interesting question. Can it think? Can it feel? Can it fix itself if something actually happens to it? So one more graph on the trends of semiconductors and how they've grown, because there's a couple important things on this graph. 42 years of microprocessor data. In the transistors in the thousands, you can see the red triangles, right? We have seen Moore's Law. We already demonstrated that it is following it. But a couple other things are happening. Even though transistors are getting smaller, single thread performance is starting to taper off, right? The frequency, the speed at which it's operating is starting to taper off. So even though you're getting smaller and smaller, there's still some performance constraints that you're dealing with. One other nice thing you're seeing is even though you're putting, orders of magnitude more transistors on a chip, the power is staying the same, which means power is trending in a good direction. It's probably not ever going to go down, but it's at least going to stay flat. Out of this, though, you do see the number of logic cores that comes with a processor, right, is starting to increase. You think about this. In the beginning, you had 1 or 2 parallel processing cores. Now you have upwards of, you may have 100 to 200 processing cores. So there's a couple ways now that we're starting to increase performance. One of it is the logic cores, because we know that the frequency and the clock speed staying the same. We know that a single one is staying, we aren't seeing markedly increased performance. So transistors, so the increase in performance now is tied to the number of logic cores and the number of transistors. So what's our take-home lesson from this? Absolutely, Moore's law exists. Computers double in transistor count every 2 years. But the other thing I wanted to bring back to you is there was virtually no capability from a computer standpoint when AI was invented. AI has been around a long time. Semiconductors have been around a long time. It's only now that they're starting to converge against each other so you can actually make progress. Right, chapter 3. I want to talk a little bit about semiconductor manufacturing, which is fairly important to this, because as we get into heterogeneous integration, you have to have a basic understanding of actually what is happening, how semiconductors are manufactured. Many of you may have this, and this is your chance to take a break if you already understand this. Many of you may understand it better for me than I do, but for some of you, I want to make sure you understand how semiconductors are manufactured. Manufactured in extremely expensive and complex facilities, $5 to $10 billion, maybe more now. It depends on the price of equipment. They're massive clean rooms with incredibly expensive machines that sequentially process the semiconductor to arrive at the functionality that's required. There are a variety of processes, and I'm going to hit on some of them a little bit more than others. It starts with an ingot of silicon. The silicon is diced and then it's polished. You have a silicon dioxide deposition on it, which flattens out the surface and makes you be able to grow on it. And then you actually start with what's called a resist. You put a resist on and you move into one of the most complicated processes of the semiconductor manufacturing, which is lithography. Lithography is a process of taking your design. So your design's been built computationally. You have a reticle, which is called a mask. You shine the light through it and you expose your photoresist, right? So you're starting to do patterning on the chips, right? Think about this though, and we're going to talk a little bit more about the size. Right now in your Intel i7, the size of your transistors is 5 nanometers, right? So think about the size of a green photon. A green photon is 532 nanometers. So you're almost 100 times smaller than a green photon in a single transistor. So think about the types of engineering that goes into taking light, passing it through a reticle, focusing it down on the wafer so that you can map out the processes that are going to be required on a 5 nanometer basis. It's incredible. Lithography is an amazing process, right? So you do lithography, you remove whatever photoresist isn't there. You may have to do ion implantation. You may have to do etch, right? You take the resist off and you start all over again. You may do this 40 to 100 times to build a single device in the fab. It is incredibly proprietary, controlled, and efficiencies and effectiveness are driven maniacally by Intel and TSMC, right? They have to drive up yields, they have to drive up performance, they have to drive up throughput because there is insatiable demand for semiconductors. This is an amazing field that continues to advance at a rapid rate. Now, evolution of the node size, and this is one of the reasons that Moore's law continues to accelerate so rapidly, right? Let's go back to 2005. We were talking about 90 nanometer gates, right? 90 nanometer gates. But in your old cars, like your 1980 Chevy that had some of its first computers, you were talking 2 and 4 micron transistor sizes. 2005, we're talking 90 nanometer transistor sizes. 2020, and here we're at 5 nanometer now. They're actually moving into 18 angstrom devices to continue to shrink the size of the next generation node. course, if you shrink the size, you're able to get more transistors in a certain area. You shrink the size, you decrease power. But this has been a continuing battle. Moore's law continues to go, and a lot of it is due to the shrinking of the transistors. When this is all done, this is a 300 millimeter wafer. This is a completed wafer. You can see what's been created here, multiple devices on this. It's actually then diced, repackaged individually. These may be CPUs or some other device, and you can see how many are made on a 300 millimeter wafer. This is a cross section. I wanted to show you all the different layers, or an idea of some of the different layers. This is a very generic. This is a very generic image on the left-hand side. The right-hand side is an actual cross section of a semiconductor taken with a scanning electron microscope. This is an idea of what it looks like when you're done with all those processes. What I wanted to show you here, though, are really what you want to call the three parts of the semiconductor. You have the front end of the line. This is where the transistors live, right? So this is where some of the complicated processing is done. This is where you have to do ion implantation to dope your transistors so you can actually get semiconductive properties. Those have a variety of different layers in them, as you can see. And of course, like I said, there's many different types, and we don't have time to get into them. They all have different configurations depending on sizes. But you can see there are many, many processes down in here to build this. Then you get into this is all the front end of the line. Then you get into the back end of the line, which are layers of copper. A lot of, well, it used to be aluminum. Now a lot of it's mostly copper. You have copper back end of line, which allows you to implement all the logic that you have. And then you have to have the interconnects, which tie all the logic to the rest of the system. And you do this through solder bumps. Like I said, this is the processing is incredibly complex to get to this point, but it's remarkable that the performance of the machines and the capability of the organizations that build these devices. So your take-home lesson from this is semiconductors are incredibly complex to manufacture. Moore's law has been primarily fulfilled through miniaturization, and large monolithic chips, as you can see, are increasingly more difficult to reliably manufacture. The smaller the chip, typically the higher the yield. Let's go to chapter 4, classic 2D integration. And I'm sure most of you know what 2D integration is. But in the past, and most of us have grown up with this, and this is a standard motherboard, this is how you integrated semiconductors, right? Here was your CPU. It was then tied to all the other devices through a variety of other peripherals. The one take-home lesson from this slide is, though, here's your CPU, sits out in the middle, but this is how it's tied to its RAM, right? The RAM sits in a perpendicular stack through another set of interconnects. It is neither close, right? It's not really close to the CPU in electron time. There's a lot of power that takes to move that distance. And once again, you're going through a circuit board here, the blue circuit board, you're going through a variety of interconnects, and you're also going through a whole nother circuit board that the memory is mounted on. That leaves a couple things. One is tremendous power consumption, but also time delay. If you're an electron, it's much easier to go a few millimeters than in this case to go a few inches. So the lesson from this is, this is not the lesson that I wanted to have here. I must have switched my slides. The lesson from here is there are efficiencies to be gained from using our standing configuration of printed circuit boards, right? There are ways to make this better. And how we make this better is through advanced packaging and heterogeneous integration. Next chapter. Now, this is where it starts to really get complicated. I want to talk to you, and once again, there may be some of you on this call that are much more aware of the ontology and the applications of AI than I am, but I wanted to touch on just how diverse AI actually is. People talk about AI, but there's many, many classes of AI. They have wildly different requirements, right? So let's just look at this. This is a fairly well-accepted ontology of AI. Machine learning. For me, machine learning is the easiest to understand, right? It's multivariate analysis. You have a dependent variable, a bunch of independent variables, and you want to figure out what's the response of one, assuming that a bunch of them behave in a certain way. But there's also others. There's natural language processing, right? We know we've seen Chat GPT. We know exactly how powerful that is, right? So there's contract extraction, there's translation. It's able to answer questions. It's able to write papers for you. It's remarkable. A whole different animal, though, than matrix algebra, right? It's a complete different animal. You have to have knowledge engines. You have to have inference engine. You have to use the cloud. So it's a whole different computing structure. You have expert systems to solve problems in certain areas. So these have a variety of different configurations. We all know there's image recognition, machine vision. We see them in cars, right? We see that in facial recognition. Depends whether it's video or whether it's still. It depends whether you're looking at faces, whether you're looking at complex rules for autonomous driving, right? Once again, even though they're all grouped under AI, the hardware required and the processing required is extraordinarily different and difficult. We know that there's speech, there's planning, there's robotics, and once again, planning, like expert systems, depending what you're planning and what you're doing, it may require a whole different set of inputs and operations. So let's just look into, and I want to do this because it defines to you the complexity of the math that's required for artificial intelligence. Let's look at the first branch of machine learning. We have supervised learning. We have a continuous target variable. We're going to use multiple regression so that it picks stock prices, right? This is a pretty easy problem to understand. I know if certain things potentially happen that the stock price is going to do this. But the thing is, maybe there's 10,000 variables that affect stock price. And I want to estimate what's going to happen in the stock market and what's going to happen in stock prices so I can do reasonable trading. Well, first of all, you have to know what those variables are. You have to have access to a beta database of what that performance has been. But then you also have to calculate quickly. I'm not sure how many of you have gotten through linear algebra and multiple regression yet, but really, if Y is the stock price, right, you have basically Y is built, the value of Y is built up from a value of basically a bunch of interactive lines, right? You have a slope and you have a variable. The only way to solve this is through matrix algebra. And the size of the matrix is actually the number of variables you have. So if you have 10,000 variables that you are trying to assess against stock price, well, then the matrix that you have to solve is 10,000 by 10,000. And I'm sure all of you have had the opportunity to solve matrices by hand. It's not fun. And it gets much more complicated depending on how many variables that you have in place. So you think about the type of computer that would invert a 10,000 by 10,000 matrix, and it's massive. And that's where you get into different types of processors like FPGAs, GPUs, depending on what you're trying to do. So the point that I want you to take home from this is you have a variety of different AI, right? AI means so much, but you also have different types of processors that are actually suited for different types of mathematical functions. So where you have your CPU, which can do some types of AI, but not much because it's not suited to it. You also have the GPUs, the FPGAs, the VPUs, right? You have these different types of computational units that then have to be customized to support your different specific AI application, right? AI applications are extraordinarily diverse and complicated, and you have to be able to customize your hardware to rapidly and effectively perform your computation. And that's not simple because, as you know, I just showed you how semiconductors are made. You can't go in and build a custom chip every time you have a custom AI application. One of the most shocking things I've heard in years, the chip that sits in your cell phone, right? Your NVIDIA chip in your cell phone took 2,000 man years to design, and they did it over 18 months. So think about that. You basically have 3,000 engineers working for 18 months to design your NVIDIA chip. These are not low-end designers. These are extremely high-end designers. And you have to build this, and you have to build the mask, and you have to develop the processes behind it. This is a multi-billion-dollar exercise to make the chip, the primary chip that operates in your phone. So you have to have flexibility, right? You have to be able to customize your devices so you can still maintain efficiency and accuracy, but yet get the correct computational elements in place to support your application. All right, so you've seen 2D integration, right? It's basically you put your chips on printed circuit boards. They're multiple layers. You know there's certain loss. They've been tremendous for years, right? We've all learned how to design printed circuit boards, populate them. Heck, whenever I started, you actually had pins on your chips and you had socket mounts. So you could pry your integrated circuits on and off your circuit board. But there was loss, there was cost in it. So when they started soldering them directly to printed circuit boards. So now let's talk about exactly what 2.5D integration means, and then ultimately what 3.5D integration means. All right, 2.5D integration. It's very simple. Instead of using a printed circuit board, use a glass interposer, right? You mount your chips, and you can do it a variety of different types of chips. You mount them directly to the glass interposer. So you have a variety of bump bombs on the bottom. It's many, many different ways to integrate. You have through silicon vias, so it allows you to do flip chip or other types of bonding. But in reality, you're taking the printed circuit board and now you're compressing it. So instead of running through inches of copper, you're running through maybe millimeters of copper. So right off the bat, you're decreasing latency. And think about it. If you're an electron and you have to make a trip, I don't know, 1 billion times over 3 inches or make it 1 billion times over 2 millimeters, there's a massive difference, right? You can now also mount different types of chips. Now you, of course, could do that on a circuit board, but you had latency, right? So now you can start to mount your basic CPU, your memory, your DSP, your FPGAs. You can now start to mount these all in what's called a silicon interposer. It's glass. It's made specifically for the application. And then you're able to take the glass interposer. It helps with heat mitigation. It helps with integration in general. And then you put it down on your packaging substrate. So this is called chiplets, right? You have bits and pieces of different types of functionality that you can put together. And if you're doing something really complex and you don't have the money to build your custom processors, well, now you start to pick and choose pieces and you can start to put them together like Lego blocks to customize your application. Obviously, it's not as simple as Lego blocks, but the opportunity is there to now customize your application. Now, you also hear about 3D. 3D is now you have your memory, right? I showed you how you plugged your memory cards into your motherboard. We've talked about the latency. But now, what if you can now actually stack your memory and set it right next to your processors so that there's no latency, that you can manage the heat, and you can stack it up. So you can get extraordinarily dense memory in a certain area. It's remarkable. And now, this is some of the next step in semiconductor packaging. So let's get back and pull up a different look at Moore's Law. This is actually pretty remarkable. So if you look down here in the 70s and 80s, here are your microprocessors. My beloved 8086 that I started using early on. It was one of the greatest things in the world. Maybe it worked at 3 megahertz. It depended. You got up to the 8486, you were probably up around 10 megahertz. It was the greatest thing in the world. But this is your CPUs, right? Then the GPUs came on in the mid-90s, and they started to accelerate so you could get transistor count up. Then you moved to AI accelerators, right? So you can see that we're going through these evolutions of different types of technologies and packaging to get into a certain area. EMIB, which is Intel's heterogeneous integration, you can see now you're starting to get just a little bit off the line, right? Here's a bump. So across the years, there's this divergence starting to happen across the line, and now it's due to this. Now let's look at the red triangle. Chip on wafer on substrate. Look at what's happened over the course of a couple years. You get an order of magnitude increase now, right? An order of magnitude increase in what you're able to do. And it's not just in transistor count. This is an order of magnitude in performance in many cases too. We're also going to talk about the Cerberus at the end of the talk here. It'll be the last thing we address, but it's a huge wafer scale computing. So let's look at the evolution here. Now, this is out of TSMC, and you think about the primary players in advanced packaging. I first go to Intel, TSMC, and AMD, and NVIDIA, right? Those are your four primary semiconductor manufacturers. Let's look at how fast this is moving. 2016, we just started a little bit of packaging. Your interposer area is 1.5 compared to what it was in Gen 1 in 2011. But really, this is only starting to happen here over the last few years. The interposer is doubled in size from 16 to 18. You have 48 gig of memory. Get up here to 2021, 2 years later, 128 gig of memory. It's 3x in interposer size. And in 2023, you're probably going to get to somewhere around 6x, right? What I wanted to show you then is I extracted this from elsewhere. This table isn't from the slide, but you can see in 2020, the bandwidth moves to 2.7 terabits per second. That is a remarkable amount of information being moved. You think about something like a matrix calculation, that's where it's really critical to be able to move information around rapidly and do your computation. What TSMC calls this is chip on wafer on substrate. Everybody has different names for it. Of course, there's different measures of performance, but all in all, if you dig into it a little bit, you can figure out how they compare to each other, right? So advantages to advanced packaging, right? Obviously, improved speed, increased transistor count. You either have level or reduced power consumption, right? Because you're not moving electrons a long distance, because you do have smaller transistors over time. It's flexible, right? You don't have to build custom chips like you do for a cell phone. If you have an application, you may be able to cobble something incredibly effective together for a fraction of the price you would have if you build a custom ASICs. Also, if you go smaller and smaller, if you're able to put different size chips together without suffering a performance penalty, then your yield goes up and your costs go down, because you're not building one inch chips, which have lots of issues, particularly in lithography and in yield, right? So advanced packaging has significant advantages, and you saw it in the gain, the whole 1 to 2 decade gain in performance against Moore's law. Let's look at where we get near the end here. Some examples powering AI explosion. Hopefully some of you have got to work on this. Let's look at Intel. Intel is Foveros. Intel calls their advanced packaging EBID in Foveros, right? But you can see how this has progressed. And one of the things that I wanted you to take home from this is you start to see increased gains in advanced packaging by decreases in the size of the bonds, right? If your bump bond's big, if your bump pitch is big, which is what you use, that's your solder bump that you saw on the top of that one image on the left. If your solder bump decreases, it gets smaller and smaller in size, you have less heat, you have loss, but you can also get denser, right? You can get denser integration. Now we're down to the point where we have 10 micron bump bond, which is pretty small, and you can start to get denser integration on your chip. Decreases size, right? Decreases size, decreases how far the electrons have to move. Now we're also having hybrid. So now you're starting to put light, right? You can start to put light into and out of the chips. This is remarkable. So just real quick on Foveros again, it's very sexy. It's a great looking chip, but here's a cross section of what this might look like. Here's your base logic, maybe your CPU, but you have an FPGA sitting on top of it, right next against it. Right here, you have another base die, but you also have your memory right next against it. And now you can start to map this out, whether it's CPU, GPU, FPGA, right? You can start to put these together. You can be flexible, heterogeneous, right? This is the heterogeneous integration part of this. Now, it's not without complication. There's a lot of through silicon vias, right? It depends whether you flip chip bond or whether you put them on facing down, right? So sometimes you have to have through silicon vias. You have to make sure that these all line up appropriately. You have to bond them appropriately. So they're not without challenges, but those big three are making incredible gains at the moment. Last one, and we'll start. Well, we won't. I'll make this the last commercial one we look at in lieu of time. This is the NVIDIA, right? NVIDIA is blowing up. Stock prices through the roof. They can't get enough volume. They're kicking it on AI chips. But take a look at the performance of the NVIDIA H100. 4 petaflops of 8-position floating point, or 60 teraflops of 64 digit floating point. 4 petaflops, right? Think about exactly what that means. That is astounding performance. And you can't get that in a monolithic system very easily. So this now opens up our ability now that we have data, we have the ability to store data. Now we can start to do some of the complex mathematical calculations that are required on the back end to really expedite and make more accurate, more compelling AI. We're going to skip past. We're going to skip past AMD, not because I don't like AMD, but because very similar to Intel and TSMC. But look at what happens now. A wafer scale engine. This comes from a company called Cerebus. They are now building a wafer scale AI that has 4 trillion transistors on it. Has 900,000 cores that you can parallelize to do computing, which equates to 125 petaflops of peak AI performance. Now you can start to stack all some of these up and think of the gains that you can start to make in AI, right? And the types of calculations that can be done with this sort of computing power. So this was my story. I wanted to show you guys and ladies how AI has been around a long time, but it only was able to catch up whenever we had data, when we had storage, and we had massive computing power, communication bandwidth, right? Had to be able to move this data, had to be able to get to this data, because one thing we didn't get into, remember, a lot of applications are stored in the cloud, right? So you have to send your data, you have to send your situations out, right? There's hybrids where sometimes you have knowledge engines and inference engines in different places, but you still require massive storage, massive data, and communication and computing, right? So achieving Moore's law through miniaturization, people have been threatening this for years, but we're getting down to the point where it's getting harder and harder, and not necessarily as much harder and harder, as more and more expensive. $1 billion fab at 7 or 10 nanometers costs billions and billions, maybe 10 to 15 billion at 18 angstroms, right? So the smaller you get, the prices go exponentially. But maybe you don't have to go smaller, because I showed you, you had those massive bumps with Foveros and chip on wafer on substrate, right? Heterogeneous integration provides increases in performance, flexibility, power, and cost. So this is how this all fits together. This is why we're starting to see this amazing, what I say, revolution in AI, because now the hardware exists to support it. So I talked a lot. Hopefully some of you have some questions, and hopefully I can answer them for you.
Yeah, we'll start off here with the questions. Again, just another open round. If anybody wants to submit anything, please post them in the chat. I'll be reading through. But I did have one question to kind of start this off that was kind of going around in my head as you were talking in regards to Moore's law. So as we go forward with a lot of these semiconductor manufacturers in terms of how they're building these chips now with a lot of new techniques, like mentioned with a lot of the 3D stacking that we've seen from AMD, from NVIDIA, and Intel now, and also some of the huge dumps like recently NVIDIA with, they announced their Blackwell platform 4 days ago. The B200 chip has I think it's 208 billion transistors and 20 petaflops. I guess my question more so is, do you believe Moore's law is still holding up? Is it still a thing, or is it something is it still relevant now in 2024?
So yes, right? Obviously, if you read chip wars, you'll find that people have been questioning Moore's law for a long time. Can we keep getting smaller and smaller and smaller, right? And we see this continuous path along Moore's law. I think in my opinion, and this is simply my opinion, that cost becomes important in this, right? We have this whole democratization and globalization of technology, which means a lot of people utilize their devices in different ways, and there's different markets, and you really need to address all these markets. If the costs get too high, you have to start to think about whether the enhanced performance actually is worth the cost, right? So there's always going to be a market for some of the lower nodes. And we think about what happened during COVID, whenever the automobile market came to a grinding halt, because we actually couldn't get some of the state of the practice and the older nodes that were required to operate machines. So yes, I believe that Moore's law, people will continue to pursue Moore's law. I think that advanced packaging and heterogeneous integration is a nice add-on to it. Like I said, you're going to get a few orders of magnitude difference in gain against Moore's law, but I'm guessing that they're going to continue to pursue the decrease in transistor size until it becomes cost prohibitive.
All right. One question here we have from Jason Comstock, and I apologize in advance if I butcher anybody's names. How will the advent of quantum computing affect the chip maker market? Will the chips you show become legacy almost instantly once quantum computing becomes mainstream?
This is one of my favorite questions. So I'm glad that it percolated to the top of the pile, because I've spent a lot of time trying to understand this. And one of the other jobs I have besides CEO of ARIs, I get to be a tech scout for DARPA, right? So I get to meet with a tremendous number of incredibly bright individuals, and I get to listen to their technologies, and I get to then help them understand the defense industrial complex and defense research and the types of things that need to be done to sell their story. So quantum computing, of course, has tremendous progress, right? In qubits, in my simplest mind, are probabilistic computers, right? So one of the things that quantum can do is be able to be your random number generator, right? And this is how, if you think about how a random number is generated, it requires a great deal of computation inside a computer. And it requires a lot of transistors, it requires a lot of gates, a lot of logic. If you can now then start to take some of your probabilistic computing, right, and move it away from a random number generator to a true probabilistic computer, yes. And that suits my background, because my background has been a lot of computation and simulation. So, you know, I'll give you an example. One of the first things I ever did was do light distributions in tissue, right? So you have to do a tremendous number of random walks. Well, that's not fast. It would take days on a 30 megahertz computer to do that. But now whenever you start to look at more complex simulations like that, or complex simulations like maybe I want to have a hypersonics engagement, probabilistic computing is going to greatly increase the capabilities of that numerical simulation, because you're not going through all the random number generators, and you have true probabilistic generators that you can plug back into your simulation. Now that's my understanding, and I've gone through this with many people. So if it's incorrect, I would love to hear more people's opinion on this.
All right. Another person here, Shabasis. Again, I apologize if I butchered any name. Roy. Does the latency time decrease by going from electron transport to photon?
Well, it depends, right? I think the interface is one of the challenges, certainly, right? Light is very fast, and they're making great gains in that arena. I mean, a lot of the transition is done in different types of modulators, right? Lithium niobate has been used for years in the communication sector to move the photons into electrons, and vice versa. There are a variety of different efforts that are going on in photonic computing so that transition is done more effectively, and some of the computing is done at the photon level, which, yes, inherently is expected to be faster.
All right. One more here, Sanwa. I am wondering what would particularly inhibit the acceleration of any ML or AI in the manufacturing process. Hacking the primary chip?
I'm not sure I'm following that one, Jawan. You're going to have to read that one to me again.
Yeah, no problem. I think what they're trying to ask here, is there anything in the manufacturing process that would inhibit the acceleration of a lot of the AI ML models that are currently out there? Is there anything that would cause anything to slow down, I guess, is what they're trying to ask.
You know, I think I would fall back to just looking at the history of TSMC and Intel and AMD and NVIDIA, right? Hardly anything slows these organizations down. They are some of the smartest, most innovative and effective organizations you will ever find. And I think through the years, if you go back and you look at the history, many people have believed you've been up against the last node, right? You've been up against the last speed, but there's always a way to seem to find more speed. I don't know what that is, but I think you have to look at this historically and realize that they are going to continue to innovate and drive competition forward. And a lot of it's based on economics, right? This is an extraordinarily lucrative business. It is extremely competitive. If you do pick up chip wars, you will find out just how cutthroat the semiconductor industry is, and how, you know, it is a true concept of frenemies, right? you work together one day and the next day you're competing against each other. So I would expect that those companies will continue to make tremendous gains, especially in advanced packaging and heterogeneous integration. There are a lot of gains to be made there, particularly in the process and the innovations that are used. A lot of it resembles back end of line processing, so they're very, very good at it. Some of it relies upon very precise alignment, which once again they're getting better and better at.
All right. Well, I'll do this last one, and I think we're going to wrap up from here. This is from Catherine O'Neill, and this might relate to the previous quantum computing question that was answered, but I'm going to ask it anyway. I was wondering what your thoughts are on perhaps offloading some computation needed in training AI to quantum computers, which of course come with their own hardware challenges. Do you see potential in merging quantum computing with AI?
I do, absolutely, right? I mean, particularly when it comes to multivariate analysis and probabilistic computing, and yeah, absolutely. I mean, as we talked about, there's a variety of different types of AI, and some are going to be much better suited to quantum computing than others.
All right, then. I think we're going to wrap up the questions from here because we are getting close to time, sadly. Any future questions, we'll take those into account. And Dr. Kiser, if you're okay with that, send some of them your way for answering.
Absolutely. I really appreciate everybody sticking around. It looks like people stuck around. I really hope that it gives you some food for thought. It excites you for a career, and it allows you to, catch up on some of the things you might not have seen in your classroom. So I appreciate your time, particularly as it gets close to weekend. I know what that means as a student. So thank you very much.
All right. Thank you again, Dr. Kiser, for doing this talk for us. Some last things I wanted to push real quick before we end off here. Some events we have coming up. So tomorrow, for anybody in the Purdue area, we will be at Purdue RoboMasters. This is a Midwest conference. We'll be showing up, giving a keynote speech, and also hanging around there. So if anybody's going to be in the area, feel free to stop by, check out our booth. The other thing we have going on actually next week for anybody in the OSU area, we're having a esports arena showcase in partnership with U.S. Army DEFCON Ground Vehicle System Center. Some cool virtual reality demos. We're going to have some gaming tournaments as well for anybody that's into gaming. So if anybody's interested in that, feel free to scan that QR code right there on this slide. Also as well, I'll be throwing the link in chat for anybody who can't scan that right now. If you are interested and you are in the OSU area. Outside of that, again, I'll be showing our final slide here, QR code if you want to schedule time with our student outreach coordinator. Also, as well, reach out to outreach@aifutures.us if you're not able to scan that QR code for us to follow up with you. So that's all I have. Again, thank you again to Dr. Kiser for doing this talk for us, and hope you guys have a great weekend.